The screen gathers light slowly, as though drawn from the depths of space itself, and the silence settles with the weight of distance. Perhaps you have dimmed the room, expanded the frame to fill your view, allowed the world beyond this moment to recede. There is no urgency here, only the patient unfolding of a question older than any civilization, older than language itself. If you find value in this journey, a quiet gesture of support, a subscription, costs nothing but a moment and allows explorations like this to continue. But that is a choice made in your own time. For now, there's only the vast, the distant, and the search that has no end. The universe does not withhold its secrets out of malice or intent. It is simply large beyond language, old beyond memory, and indifferent to the scales at which human thought operates. Every star visible to the naked eye is a sphere of fusing hydrogen, converting mass into light across millions or billions of years, and around many of those stars, worlds turn in silence. Some are barren, some are molten, some are wrapped in crushing atmospheres of gas or hung in frozen orbits where sunlight is a rumor. And some, a rare few, occupy a region of space so finely tuned, so balanced between heat and cold, between radiation and shelter, that liquid water can persist on their surfaces for geologic ages. These are the places where life, as it is understood through the single example available, might take root. The search for such worlds, and the effort to understand what makes them not only habitable, but perhaps more conducive to life than Earth itself, forms one of the deepest threads in contemporary astronomy. It is a search conducted not with footsteps or probes sent across the light years, but with instruments that gather the faintest whispers of infrared radiation, instruments that translate heat into knowledge, distance into data, and time into insight. Among these, the James Webb Space Telescope stands as the most sensitive eye humanity has yet opened to the cosmos, a machine designed not to see surfaces or shapes, but to read the atmospheres of distant worlds, to detect the chemical signatures that might betray the presence of biology, and to peer into the formation zones of planets still coalescing from disks of dust and gas around young stars. Before the question of life elsewhere can be pursued, the nature of habitability must be understood from its foundations. A planet does not become habitable by chance alone. It is the product of a cascade of conditions, each dependent on the others, each tuned by forces that operate over distances measured in astronomical units and timescales measured in millions of years. The most familiar framing is the habitable zone, sometimes called the Goldilocks zone, a band of orbital distances around a star where temperatures permit liquid water to exist on a planetary surface. This zone is not a fixed width. It shifts inward or outward depending on the luminosity of the star, which itself is a function of the star's mass, age, and composition. A star like the Sun, a G-type main sequence star, radiates energy steadily for billions of years, and its habitable zone lies roughly where Earth orbits, extending somewhat into the orbits of Venus and Mars. A smaller, cooler star, an M-dwarf, emits far less light, and its habitable zone contracts to a narrow ring much closer to the star, so close that a planet there might complete an orbit in a matter of days rather than a year. A larger, hotter star, such as an A-type or F-type, pushes the habitable zone farther out, but such stars burn through their fuel rapidly, offering only a brief window, geologically speaking, in which life might arise before the star exhausts its hydrogen and expands into a red giant. The concept of the habitable zone is foundational, but it is also insufficient. A planet positioned within this zone does not automatically possess liquid water on its surface. It must have an atmosphere, and that atmosphere must exert sufficient pressure to prevent water from boiling away into space or freezing into permanent ice. The atmosphere must be retained against the relentless pressure of stellar wind, the stream of charged particles that flows outward from every star. This retention depends on the planet's mass, which determines its gravitational pull, and on the presence or absence of a magnetic field, which can deflect ionizing radiation that would otherwise strip away atmospheric molecules over millions of years. The composition of the atmosphere matters as well. Carbon dioxide, methane, water vapor, and other greenhouse gases trap heat, warming the surface beyond what stellar radiation alone would provide. Too little of these gases, and a planet freezes. Too much, and a runaway greenhouse effect can render the surface uninhabitable, as happened on Venus, a world that lies within the outer edge of the sun's habitable zone, but whose surface is hot enough to melt lead, its atmosphere a choking pressure of carbon dioxide and sulfuric acid clouds. Water itself must arrive somehow. A planet does not form with oceans already in place. During the chaotic early phases of a planetary system, when rocky worlds are coalescing from the protoplanetary disk, temperatures in the inner regions are too high for water ice to condense. Water is delivered later, either by comets, which are rich in ice and form in the cold outer reaches of a system, or by asteroids that contain hydrated minerals. The timing and quantity of this delivery are sensitive to the architecture of the planetary system, particularly the presence of giant planets farther out, whose gravity can fling comets and asteroids inward or eject them entirely. Jupiter, in our own system, acts as both protector and threat, sometimes deflecting impactors that might strike Earth, sometimes hurling them toward the inner planets. The presence of a Jupiter-like giant, positioned at the right distance and the right time, may be a requirement for habitability, or it may be a hazard. The data remain incomplete, and each new exoplanetary system discovered adds complexity rather than clarity. The surface of a habitable planet must be neither entirely ocean nor entirely land. Too much water, and there are no continents, no weathering of rock to recycle nutrients, no coastal zones where tides and chemistry can interact. Too little water, and the planet becomes arid, with limited environments for life to diversify. The balance is maintained by plate tectonics, the slow churning of a planet's outer shell driven by heat from the interior. Tectonics recycle carbon between the atmosphere and the crust, regulate temperature over geologic time, and create varied topography, mountains and valleys and ocean basins, each a distinct habitat. Earth's tectonics are powered by the decay of radioactive elements deep within the mantle and core, and by the residual heat left over from the planet's violent formation. A planet too small cools too quickly, its interior solidifying, its magnetic field dying, its surface locked in place. A planet too large may have tectonics that are too vigorous, with volcanic outgassing overwhelming the atmosphere or constant upheaval preventing stable environments. The range of masses and compositions that permit sustained tectonics is not yet known with precision, but it is likely narrow. Life, at least as it exists on Earth, requires not only water and moderate temperatures, but also a suite of chemical elements. Carbon forms the backbone of organic molecules, capable of bonding in chains and rings of immense variety. Nitrogen is essential for amino acids and nucleotides. Phosphorus is needed for energy transfer and genetic material. Sulfur, iron, magnesium, calcium, and trace metals all play roles in biochemistry. These elements must be present in accessible forms, dissolved in water, or available in minerals that life can interact with. They are produced in stars, synthesized in the nuclear furnaces of stellar cores, and scattered into space by supernova explosions, and their abundances vary across the galaxy, depending on the history of star formation in a given region. A planet forming in a metal-poor region, where few heavy elements exist, may lack the raw materials for complex chemistry. A planet forming in a metal-rich region may have an abundance of iron and silicon, leading to a large core and strong magnetic field, but the ratios of lighter elements like carbon and oxygen can vary widely, influencing the types of minerals that form and the chemistry of any atmosphere. The stability of a star, the architecture of a planetary system, the delivery of water, the presence of tectonics, the availability of essential elements, and the retention of an atmosphere are all necessary, but not sufficient. Time is required. Life on Earth did not appear instantly. The planet formed roughly 4.5 billion years ago, and the oldest evidence of life, in the form of isotopic signatures in ancient rocks, dates to perhaps 3.8 billion years ago, possibly earlier. This suggests that life arose relatively quickly, within a few 100 million years of the surface cooling enough for liquid water to persist. But the transition from simple, single-celled organisms to complex multicellular life took far longer, nearly 3 billion years, and the emergence of intelligent, technological beings required almost the entire age of the planet. A habitable world must remain habitable for billions of years, which imposes constraints on the longevity and steadiness of its star, the stability of its orbit, and the buffering capacity of its climate system against perturbations. When astronomers speak of habitable exoplanets, they are referring to worlds that meet these criteria, or at least a subset of them, to the best extent that can be inferred from observations. The first exoplanet orbiting a Sun-like star was confirmed in 1995, a gas giant larger than Jupiter, orbiting so close to its star that it completed each orbit in a matter of days, its atmosphere heated to thousands of degrees. This was not a place for life, but it was a revelation. Planets existed around other stars, and they came in configurations unlike anything in our solar system. Over the decades since, thousands of exoplanets have been cataloged, detected primarily through two methods. The radial velocity method measures the wobble of a star caused by the gravitational tug of an orbiting planet, a wobble that shifts the star's light toward the red or blue end of the spectrum in a periodic rhythm. The transit method measures the dimming of a star's light when a planet passes in front of it, blocking a tiny fraction of the light. The amount of dimming reveals the planet's size, and the timing reveals its orbital period. Combining these methods with additional observations, astronomers can infer a planet's mass, radius, density, and sometimes the composition of its atmosphere, if the planet transits its star and some of the starlight filters through the atmospheric limb, where molecules absorb specific wavelengths. Among the thousands of known exoplanets, a subset occupies the habitable zones of their stars. These are the targets of greatest interest, the worlds where liquid water might pool, where atmospheres might contain oxygen or methane or other gases that could be produced by living organisms. But the designation of a planet as habitable does not mean it is inhabited, nor does it mean it is Earth-like. Many habitable zone planets are significantly larger than Earth, with masses several times greater, thick atmospheres, and compositions that may include vast amounts of water, resulting in planets covered entirely by deep oceans with no solid surface accessible. Others are smaller, with thin atmospheres or none at all, their surfaces scorched by radiation from active young stars, or frozen in tidally locked rotations where one hemisphere eternally faces the star and the other faces the void. The diversity is overwhelming, and the task of determining which of these worlds might actually host life is only beginning. This is where the concept of superhabitability enters the discourse, a refinement of the habitable zone framework that asks not merely which planets could support life, but which planets might support life more readily, more abundantly, or more persistently than Earth itself. The idea challenges the assumption that Earth represents the optimal template for habitability. Earth is habitable, certainly, and it is the only known inhabited world, but is not necessarily the best possible world for life. Its orbit is nearly circular, but not perfectly so. Its axial tilt produces seasons, which drive climatic variability, sometimes to extremes. Its moon stabilizes that tilt, preventing chaotic oscillations, but the moon's formation, the result of a colossal impact early in Earth's history, was a chance event. The Sun is a G-type star, stable and long-lived, but it is more massive and hotter than the majority of stars in the galaxy, which are M-dwarfs, cooler and longer-lived. Earth's size and mass are sufficient to retain an atmosphere and drive tectonics, but a planet somewhat larger, somewhat more massive, might retain its internal heat longer, sustain tectonics for a greater span of time, and provide more surface area for diverse environments. A planet orbiting a K-type star, slightly cooler and longer-lived than the Sun, might enjoy a longer window of habitable conditions, billions of years longer, allowing more time for evolution to explore complexity. The criteria for superhabitability are not yet standardized, but they converge on a set of conditions. The star should be a K-type or early M-type, with a lifespan of tens of billions of years rather than the Sun's 10 billion. The planet should be somewhat larger than Earth, perhaps 25 to 50% greater in radius, providing more surface area, stronger gravity for atmospheric retention, and a larger internal heat reservoir for prolonged geological activity. The planet should be somewhat older than Earth, old enough that any initial volatile atmosphere has stabilized, that impact from stray planetesimals have ceased, that ecosystems, if they exist, have had time to diversify and fill every available niche. The planet should have a higher mean surface temperature than Earth, not enough to prevent ice caps or high-latitude climates, but enough to encourage liquid water across a broader fraction of the surface, reducing the extent of frozen polar regions and expanding the habitable area. The planet should have greater humidity, more rainfall, more extensive networks of rivers and lakes, as water is the medium in which biochemistry operates most efficiently. The planet should possess both oceans and continents, with a ratio favoring neither extreme, and with a distribution of land masses that creates varied coastal zones, shallow seas, and island chains, all of which are biodiversity hotspots on Earth. The notion that Earth might be less habitable than other worlds is not an assertion of Earth's inadequacy, but an acknowledgement that habitability exists on a spectrum. Earth is located near the inner edge of the Sun's habitable zone, close enough that as the Sun ages and brightens, which it will continue to do over the next billion years, Earth's oceans will eventually evaporate, and the planet will transition into a Venus-like state. A superhabitable planet around a K-dwarf, by contrast, might enjoy stable conditions for 5 or 10 billion years, long after Earth has become uninhabitable. Earth's plate tectonics, while active, are not guaranteed to continue indefinitely. The planet's internal heat is finite, and there are geological scenarios in which the mantle could enter a stagnant lid regime, where the crust solidifies into a single immobile shell, ending the recycling of carbon and the regulation of climate. A larger planet, with more radioactive elements and more residual heat, might avoid this fate for far longer. Identifying superhabitable planets is a challenge that current technology is only beginning to address. Most exoplanet detections provide limited information. The transit method reveals size and orbital period, sometimes atmospheric composition, if the transit is observed with sufficient precision across multiple wavelengths. The radial velocity method reveals mass. Together, these yield density, which constrains composition, distinguishing rocky planets from gas dwarfs, but they do not reveal surface conditions, the presence of oceans, the activity of tectonics, or the chemistry of the surface and atmosphere in detail. For that, more sophisticated observations are required, and this is where infrared astronomy becomes indispensable. Infrared light occupies the portion of the electromagnetic spectrum just beyond the red end of visible light, with wavelengths ranging from about 700 nanometers to 1 millimeter. It is a radiation emitted by objects that are warm rather than hot, objects at temperatures ranging from a few degrees above absolute zero to several thousand degrees. Stars emit most of their light in visible or ultraviolet wavelengths, but planets, which do not generate light by fusion, emit in the infrared, radiating away the heat they receive from their stars and, in some cases, heat from their own interiors. By observing a planet in the infrared, astronomers can measure its temperature, study the structure of its atmosphere, detect clouds, map weather patterns, and identify the molecular species present in the air. Molecules absorb and emit infrared light at characteristic wavelengths, each species leaving a unique fingerprint. Water vapor, carbon dioxide, methane, ammonia, oxygen, ozone, and countless other compounds can be detected and quantified if the observations are precise enough. The Earth's atmosphere, however, absorbs much of the infrared radiation arriving from space, particularly at wavelengths corresponding to water vapor and carbon dioxide, which are abundant in the air. Ground-based infrared telescopes can observe only in narrow windows where the atmosphere is relatively transparent, and even then, the observations are compromised by the thermal glow of the atmosphere itself and the telescope structure. To observe the full infrared spectrum, telescopes must be placed above the atmosphere, in space, where the view is unobstructed and the background is cold. The James Webb Space Telescope was designed with this purpose foremost in mind. Launched in late 2021, it is the largest and most sensitive infrared observatory ever deployed, with a primary mirror 6.5 meters in diameter, composed of 18 hexagonal segments coated in gold to maximize reflectivity in the infrared. The telescope orbits the Sun at the second Lagrange point, a position of gravitational equilibrium roughly 1.5 million kilometers from Earth, on the far side from the Sun, where a large sun shield, the size of a tennis court, blocks the light and heat from the Sun, Earth, and Moon, keeping the instruments at temperatures near absolute zero, around minus 233 degrees Celsius. This cooling is essential, as the detectors themselves would otherwise overwhelm the faint signals from distant planets and galaxies with their own thermal emission. The James Webb Space Telescope does not take pictures in the traditional sense, though images are one product of its observations. Its primary function is spectroscopy, the dissection of light into its component wavelengths, revealing the physical and chemical properties of the objects observed. When a planet transits its star, a small amount of starlight passes through the planet's atmosphere before reaching the telescope. Molecules in the atmosphere absorb certain wavelengths, creating dips in the spectrum, and by measuring these dips, astronomers can determine which molecules are present and in what quantities. When a planet passes behind its star, an event called a secondary eclipse, the combined light of star and planet drops to just the star's light, and the difference reveals the planet's own infrared emission, its thermal spectrum, which encodes information about temperature at different altitudes and the distribution of heat between the day and night sides. The sensitivity of the James Webb Space Telescope has already transformed the study of exoplanet atmospheres in the few years since its deployment. Among its early targets was WASP 39b, a gas giant orbiting a sun-like star about 700 light-years away. The planet is slightly larger than Saturn and orbits extremely close to its star, completing each orbit in just over 4 days, with a dayside temperature exceeding 900 degrees Celsius. Observations with Webb's instruments detected water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and, unexpectedly, sulfur dioxide, a molecule produced by photochemical reactions driven by intense ultraviolet radiation from the star. This was the first detection of photochemistry on an exoplanet, a confirmation that the atmospheres of these distant worlds are dynamic, with chemical processes actively reshaping their composition. WASP 39b is not habitable, but the detection demonstrates the capability of the telescope to identify molecules that would be far more difficult to detect in the thinner atmospheres of smaller, rocky planets. Another early target was LHS 475b, a rocky planet slightly smaller than Earth, orbiting an M-dwarf star about 41 light-years away. The planet is too hot for habitability, with an orbit that takes only 2 days and a surface temperature likely in the hundreds of degrees, but it represents the type of planet that could, in other systems, occupy the habitable zone of such a star. Observations with Webb confirmed the planet's rocky nature and placed constraints on its atmosphere, ruling out thick hydrogen envelopes and suggesting either a thin atmosphere dominated by carbon dioxide or no atmosphere at all. The data are still being analyzed, but the observations illustrate the challenges of characterizing small planets around small stars, where the signals are faint and the contrast between star and planet is low. M-dwarf stars are the most abundant type of star in the galaxy, accounting for roughly 75% of all stars. They are small, with masses ranging from about 8% to 60% that of the Sun, and they burn hydrogen so slowly that their lifetimes stretch into the trillions of years for the smallest among them, far longer than the current age of the universe. Their habitable zones are close-in, which makes planets they're easier to detect and characterize, as the transit depth is larger and the orbital period is short, allowing multiple transits to be observed in a reasonable time frame. But M dwarfs present challenges for habitability. Young M dwarfs are highly active, with frequent and powerful stellar flares that release bursts of ultraviolet and X-ray radiation, potentially stripping away planetary atmospheres or sterilizing surfaces. Many M dwarfs exhibit strong magnetic activity for billions of years, far longer than Sun-like stars. Planets in the habitable zones of M dwarfs are likely to be tidally locked, with one hemisphere always facing the star and the other in permanent darkness, a configuration that could lead to extreme temperature gradients, with the day side too hot and the night side too cold, unless atmospheric circulation or a thick atmosphere redistributes heat. Despite these challenges, M dwarfs are compelling targets in the search for habitable planets because they are so numerous, because their planets are easier to observe, and because any planet that does manage to retain an atmosphere and maintain liquid water could do so for timescales far exceeding the age of the Earth. The TRAPPIST-1 system, located about 40 light-years away, is a prime example. TRAPPIST-1 is an ultra-cool M dwarf, barely larger than Jupiter, with a surface temperature of only about 2,500 Kelvin, and it hosts at least 7 Earth-sized planets, all orbiting within a distance smaller than the orbit of Mercury around the Sun. 3 of these planets, designated TRAPPIST-1 E, F, and G, orbit within the star's habitable zone, and the densities of all 7 planets suggest rocky compositions. The system is ancient, with an estimated age of 7 to 8 billion years, providing ample time for atmospheres to form, for climates to stabilize, for life to arise, if conditions permit. The James Webb Space Telescope has observed several of the TRAPPIST-1 planets, seeking to detect atmospheres and characterize their compositions. Early results for TRAPPIST-1b, the innermost planet and therefore the hottest, suggest little to no atmosphere, consistent with models predicting atmospheric loss due to stellar radiation. Observations of the cooler, potentially habitable planets are ongoing, and each new dataset refines the understanding of whether these worlds are airless, enshrouded in thick atmospheres, or possess thin, temperate envelopes that might sustain liquid water. The question of whether a planet is habitable cannot be answered by observations of the planet alone. The star dictates the environment, and stellar evolution shapes the long-term prospects for life. Stars are born from the gravitational collapse of molecular clouds, vast regions of cold gas and dust that fragment under their own weight. As a fragment contracts, it heats up, and when the core temperature reaches several million degrees, hydrogen nuclei begin to fuse into helium, releasing energy that halts the collapse and establishes hydrostatic equilibrium. The star settles onto the main sequence, a stable phase that lasts for the majority of its life, during which it fuses hydrogen in its core at a steady rate. The duration of this phase depends on the star's mass. Massive stars with tens of solar masses burn through their hydrogen in mere millions of years, expanding into supergiants and exploding as supernovae. Low-mass stars, like M dwarfs, burn hydrogen so frugally that they remain on the main sequence for trillions of years. Sun-like stars fall in between, with main sequence lifetimes of about 10 billion years. As a star ages, its luminosity increases. The Sun today is about 30% brighter than it was when it first formed, and it will continue to brighten, reaching roughly twice its current luminosity by the time it exhausts the hydrogen in its core about 5 billion years from now. This evolution shifts the habitable zone outward over time, and planets that begin at the inner edge may become too hot before the star leaves the main sequence. When the core hydrogen is depleted, the star's core contracts and heats, and hydrogen begins fusing in a shell around the core. The outer layers expand, and the star becomes a red giant, with a luminosity that can increase by factors of hundreds or thousands. For the Sun, this phase will render the inner planets, including Earth, uninhabitable, possibly even engulfing them as the outer envelope expands beyond the orbit of Venus. The habitable zone moves outward dramatically, perhaps reaching the orbits of Jupiter's or Saturn's moons, But this phase lasts only a few hundred million years before the star sheds its outer layers as a planetary nebula, and the core collapses into a white dwarf, a dense remnant that emits little light and whose habitable zone, if it could be called that, contracts to a narrow band very close to the star. Any planets that survive the red giant phase are subjected to intense radiation and tidal forces during the expansion and are unlikely to retain atmospheres or surface water. K-dwarfs, slightly cooler and less massive than the Sun, offer a middle ground. They have main sequence lifetimes of 15 to 30 billion years, long enough for biological evolution to explore countless pathways, and their luminosity increases more slowly than that of Sun-like stars, allowing planets to remain within the habitable zone for extended periods. Their habitable zones are also broader than those of M-dwarfs, reducing the likelihood of tidal locking, and they are less active, producing fewer flares and less extreme radiation. For these reasons, K-dwarfs are sometimes considered the optimal stars for hosting superhabitable planets, balancing longevity, stability, and a habitable zone that is neither too narrow nor too close to the star. The composition of a star, its metallicity in astronomical terms, meaning its abundance of elements heavier than hydrogen and helium, influences the planets that form around it. Stars with higher metallicity, meaning more carbon, oxygen, silicon, iron, and other heavy elements, are more likely to have rocky planets, as these elements are the building blocks of solid worlds. Stars with lower metallicity may form planets that are dominated by hydrogen and helium, or they may struggle to form planets at all, as the protoplanetary disk lacks sufficient solid material to coalesce into planetesimals. Metallicity varies across the galaxy, with higher abundances in the inner regions, where star formation has been ongoing for billions of years and successive generations of stars have enriched the interstellar medium with supernova ejecta, and lower abundances in the outer regions and in the halo, where the gas retains a more primordial composition. The Sun's metallicity is roughly solar by definition, but it is higher than average for stars of its age and location, and this may have contributed to the formation of the diverse planetary system we observe, with 4 rocky planets, 2 gas giants, 2 ice giants, and a rich population of asteroids and comets. Planet formation is a violent and chaotic process. A protoplanetary disk begins as a flat, rotating cloud of gas and dust surrounding a young star, with temperatures highest near the star and decreasing outward. Dust grains, microscopic particles of silicates, carbon, and ice, collide and stick together, forming larger aggregates. This process, called accretion, continues until planetesimals, bodies kilometers to hundreds of kilometers in size, emerge. Planetesimals collide and merge, building up protoplanets, and the largest of these, through runaway growth, sweep up material from their orbital zones, eventually becoming terrestrial planets in the inner disk and cores of giant planets in the outer disk. Gas giants form when a solid core reaches several Earth masses, sufficient to gravitationally capture hydrogen and helium from the surrounding disk before the disk dissipates, which happens within a few million years. Ice giants, like Uranus and Neptune, form in regions where less gas is available, where they form too late to accrete substantial envelopes before the gas is blown away by stellar winds. The architecture of a planetary system is shaped by migration, the inward or outward movement of planets due to gravitational interactions with the disk or with other planets. Massive planets, particularly gas giants, can migrate inward, clearing gaps in the disk and sometimes ending up in tight orbits very close to their stars, becoming hot Jupiters. This migration can disrupt the formation of rocky planets in the inner system, scattering or ejecting them, or it can stir up the asteroid belt, increasing collision rates and delivering water and organic material to planets that survive. Some systems undergo violent instabilities, with planets crossing each other's orbits, leading to ejections, collisions, or planets being flung into distant, eccentric orbits. The solar system is thought to have undergone such an instability early in its history, with Jupiter and Saturn's orbits shifting and triggering the late heavy bombardment, a period of intense impacts on the inner planets about 4 billion years ago. The diversity of exoplanetary systems suggests that such dynamical histories are common, and that the final architecture of a system is the result of complex, often chaotic interactions that span millions of years. A planet's habitability is also influenced by its neighbors. A large planet in an outer orbit can act as a gravitational shield, deflecting comets and asteroids that might otherwise impact inner planets, reducing the frequency of extinction-level events. Conversely, such a planet can also perturb the orbits of small bodies, sending them inward, increasing impact rates. The presence of multiple planets in a system can lead to orbital resonances, configurations where the orbital periods are related by simple ratios, such as 2 to 1 or 3 to 2. These resonances can stabilize orbits, locking planets into predictable, long-term patterns, or they can destabilize orbits if the resonance is near a chaotic boundary. The TRAPPIST. One system is an example of extensive resonances, with all 7 planets locked in a chain of near-integer period ratios, a configuration that likely stabilized early in the system's history and has persisted for billions of years. Such stability is advantageous for habitability, as it prevents close encounters between planets that could eject one of them or destabilize the orbits into high eccentricities, where the planet would experience extreme variations in stellar heating. The atmosphere of a habitable planet is its shield and its interface with the cosmos. The composition of the atmosphere determines the surface temperature through the greenhouse effect, regulates the availability of water, filters harmful radiation, and mediates the chemistry that life depends on. An atmosphere forms through outgassing from the planet's interior, as volcanoes release water vapor, carbon dioxide, sulfur dioxide, and other gases trapped in the mantle, and through the vaporization of impacting comets and asteroids. The early atmosphere of a terrestrial planet is likely dominated by hydrogen and helium captured from the protoplanetary disk, but these light gases are easily lost to space, particularly from smaller planets or planets orbiting active young stars. The secondary atmosphere, formed from outgassing and impacts, is more durable, but it too can be eroded by stellar wind, particularly if the planet lacks a magnetic field. A magnetic field is generated by the motion of electrically conducting fluid in a planet's interior, typically molten iron in the core. This motion, driven by convection as heat escapes from the core, creates electric currents, which in turn generate magnetic fields. The field extends into space, forming a magnetosphere that deflects the charged particles of the stellar wind, preventing them from directly striking the atmosphere. Earth's magnetosphere is essential for protecting the atmosphere from erosion, and the presence of a magnetosphere on an exoplanet would be a strong indicator of habitability. Detecting exoplanet magnetic fields is a formidable challenge, as the fields are weak and the signals are difficult to distinguish from stellar activity, but future observations, particularly radio observations of interactions between the magnetosphere and the stellar wind, may provide indirect evidence. The thickness and pressure of an atmosphere are determined by the balance between outgassing, atmospheric escape, and the condensation or chemical removal of certain gases. On Earth, the partial pressure of water vapor is regulated by temperature, as water condenses into clouds and precipitates as rain when the air cools. Carbon dioxide is removed from the atmosphere by weathering of silicate rocks, a process that is faster at higher temperatures, and is returned to the atmosphere by volcanic outgassing, creating a feedback loop that stabilizes temperature over geologic time. If Earth becomes too warm, weathering accelerates, removing carbon dioxide and cooling the planet. If Earth becomes too cold, weathering slows, volcanic outgassing accumulates carbon dioxide, and the planet warms. This carbonate-silicate cycle operates on timescales of hundreds of thousands to millions of years, and it requires active tectonics to recycle carbonate rocks that have been subducted into the mantle back to the surface as volcanic gases. A planet without tectonics may lose this regulatory mechanism, and its climate could become locked in a runaway state, either freezing or overheating depending on initial conditions. Oxygen is a particularly interesting atmospheric gas in the context of the search for life, as it is reactive and should not persist in large quantities in an atmosphere unless it is being continuously produced. On Earth, oxygen is produced by photosynthesis, the process by which plants, algae, and cyanobacteria convert carbon dioxide and water into organic matter and oxygen using sunlight as an energy source. The rise of oxygen in Earth's atmosphere, which began about 2.4 billion years ago, transformed the planet's surface chemistry and enabled the evolution of complex, multicellular life, which requires high levels of oxygen for aerobic respiration. The detection of oxygen in the atmosphere of an exoplanet would be a strong, though not definitive, biosignature, as there are abiotic processes that can produce oxygen, such as the photodissociation of water vapor by ultraviolet light, followed by the escape of hydrogen to space, leaving oxygen behind. Distinguishing biotic from abiotic sources requires additional context, such as the presence of other gases like methane that are out of chemical equilibrium with oxygen, or patterns in the atmospheric composition that suggest biological cycles. Methane is another gas of interest. On Earth, the majority of methane is produced by biological processes, particularly by microorganisms called methanogens that inhabit anaerobic environments like wetlands, deep oceans, and the digestive tracts of animals. Methane is also produced by geological processes, such as serpentinization, a reaction between water and ultramafic rocks that releases hydrogen, which can then react with carbon dioxide to form methane. A strong methane signal in an exoplanet atmosphere, especially in combination with oxygen or other disequilibrium gases, would warrant further investigation, but methane alone is not conclusive evidence of life. The simultaneous detection of oxygen and methane would be compelling, as these gases react with each other and would not coexist in large quantities unless continuously replenished, which on Earth is achieved by the complementary processes of photosynthesis and methanogenesis. Phosphine, a molecule composed of one phosphorus atom and 3 hydrogen atoms, has been proposed as a potential biosignature, as it is produced by certain anaerobic bacteria on Earth and is not known to be produced in significant quantities by abiotic processes under the conditions expected on rocky planets. A controversial claim of phosphine detection in the atmosphere of Venus, based on millimeter-wave observations, sparked intense debate, as Venus is considered inhospitable to life due to its extreme surface temperature and pressure, but the upper cloud layers, where temperatures are more moderate, have been speculated as potential habitat for microbial life. Subsequent observations and reanalysis of the data have cast doubt on the detection, highlighting the challenges of identifying trace gases in the atmospheres of planets where multiple chemical species and complex interactions can produce overlapping spectral features. The atmospheres of superhabitable planets might differ from Earth's in ways that enhance habitability. A slightly thicker atmosphere could provide better insulation and more stable temperatures, reducing seasonal and diurnal extremes. Higher humidity would support more extensive rainforests and wetlands, ecosystems that are among the most productive on Earth. A higher concentration of carbon dioxide, while potentially warming the planet, would also enhance photosynthesis, increasing plant growth and biomass production. The presence of clouds at various altitudes could regulate temperature by reflecting sunlight during the day and trapping heat at night, a phenomenon observed on Earth and one that exoplanet models must account for, as clouds significantly affect the thermal emission and reflected light of a planet, making spectral interpretation more complex. Planetary climates are driven by the distribution of heat, which depends on the planet's rotation rate, the tilt of its axis, the eccentricity of its orbit, and the efficiency of atmospheric circulation. A planet with a slow rotation, or one that is tidally locked, may have limited heat transport from the day side to the night side, resulting in extreme temperature contrasts. However, atmospheric models suggest that even on tidally locked planets, if the atmosphere is sufficiently thick, winds can redistribute heat, preventing the night side from freezing entirely and the day side from becoming unbearably hot. The presence of an ocean would further aid heat transport, as water has a high heat capacity and ocean currents can carry warm water toward the poles and cold water toward the equator, moderating global temperatures. Tidal locking occurs when the gravitational torque exerted by the star on the planet's equatorial bulge slows the planet's rotation until the rotation period matches the orbital period, resulting in one hemisphere always facing the star. The timescale for tidal locking depends on the planet's distance from the star, its size, and the strength of tidal dissipation within the planet, which is influenced by the planet's internal structure and the presence of oceans. Planets close to their stars, such as those in the habitable zones of M-dwarfs, are likely to become tidally locked within billions of years, if not sooner. Whether this is detrimental to habitability is debated. On one hand, tidal locking could create a permanent day-side and night-side, with extreme temperature gradients and potentially the collapse of the atmosphere onto the night side, where gases freeze out. On the other hand, models suggest that with sufficient atmospheric pressure, a global circulation pattern could establish, with winds flowing from the hot day side to the cold night side at high altitudes and returning at low altitudes, maintaining a habitable twilight zone between the two extremes, a band encircling the planet where temperatures are moderate and liquid water could persist. The tilt of a planet's rotational axis, its obliquity, introduces seasons by causing different hemispheres to receive more or less sunlight over the course of an orbit. Earth's obliquity is about 23.5 degrees, and it varies between about 22 and 24.5 degrees over a cycle of roughly 41,000 years due to gravitational interactions with the Moon and other planets. These variations influence climate on long timescales, contributing to the advance and retreat of ice ages. A planet with zero obliquity would have no seasons, and its climate would be determined solely by latitude, with the equator receiving the most sunlight year-round and the poles receiving the least. A planet with a very high obliquity, close to 90 degrees, would experience extreme seasonal variations, with each pole alternately facing the star for half the orbit and then facing away, leading to enormous temperature swings. Moderate obliquity, similar to Earth's, is thought to be advantageous for habitability, as it creates seasons that drive atmospheric and oceanic circulation without introducing extremes that could destabilize climate or prevent the persistence of life. The Moon plays a critical role in stabilizing Earth's obliquity, preventing chaotic oscillations that could occur due to gravitational perturbations from the Sun and Jupiter. Planets without large moons may experience greater variability in obliquity, with consequences for long-term climate stability. The presence of moons around habitable planets is itself a factor in habitability. Moons exert tidal forces on the planet, which can drive internal heating through tidal flexing, a process that keeps the interior molten and sustains tectonics and magnetic field generation. Tidal heating is responsible for the intense volcanic activity on Io, Jupiter's innermost large moon, and for the subsurface oceans on Europa, Ganymede, and Enceladus, moons where tidal energy maintains liquid water beneath thick ice shells despite the extreme cold of the outer solar system. A habitable planet with a large moon could benefit from tidal heating, extending the duration of geological activity. But if the moon is too large or too close, the tidal forces could be so strong that the planet is subjected to constant volcanic eruptions or tidal locking to the moon rather than the star, complicating the climate. Moons might themselves be habitable. In the solar system, Europa, Enceladus, and possibly Titan and Ganymede harbor environments where life could exist, not on their surfaces, but in subsurface oceans insulated from space by ice or, in Titan's case, beneath a hydrocarbon-rich surface and thick nitrogen atmosphere. These moons receive little sunlight, and any life there would depend on chemical energy rather than photosynthesis, but the existence of such environments expands the definition of habitability beyond the traditional habitable zone. Exomoons, moons orbiting exoplanets, are expected to be common, but they have not yet been conclusively detected, as their signals are smaller than those of the planets themselves and require extremely precise observations. The James Webb Space Telescope and future missions may be able to detect exomoons indirectly through their gravitational influence on the planet's orbit or through transits, where both planet and moon pass in front of the star, creating a complex, time-variable dimming pattern. The search for biosignatures, for signs of life in the atmospheres or surfaces of distant worlds, is one of the driving goals of exoplanet science, but it is fraught with challenges. A biosignature is any observable feature that is produced by life or that strongly suggests the presence of life. On Earth, the most obvious biosignature is the simultaneous presence of oxygen and methane in the atmosphere. But as discussed, these gases can also be produced by abiotic processes, and their detection alone is not proof of life. A more robust biosignature would be a suite of gases in chemical disequilibrium, patterns of seasonal variation that suggest biological cycles, or surface features that indicate widespread biological activity, such as vegetation. Vegetation on Earth has a distinctive reflectance spectrum, absorbing visible light strongly for photosynthesis and reflecting infrared light, creating a feature called the red edge. This spectral signature could, in principle, be detected on an exoplanet if the planet's surface is observed with sufficient resolution and contrast. However, detecting the red edge on an exoplanet is extremely difficult, as the planet's light is overwhelmed by the star's light, and the signal for vegetation would be a tiny fraction of the total reflected light. Direct imaging of exoplanets, where the light of the star is blocked by a coronagraph or star shade, allowing the planet to be seen separately, is necessary for such observations, and this requires telescopes with large mirrors and advanced instrumentation, capabilities that are being developed for future missions. The James Webb Space Telescope is not designed for direct imaging of Earth-sized planets in the habitable zones of Sun-like stars, as the angular separation and contrast are too challenging for its instrumentation. Webb is optimized for infrared spectroscopy of transiting planets, particularly those around smaller, cooler stars where the contrast is more favorable. Future space telescopes, such as the proposed Habitable World Observatory, are being designed specifically to directly image and characterize dozens of Earth-like planets in the habitable zones of nearby stars, searching for biosignatures in their atmospheres and, potentially, detecting surface features. These missions are still in the planning stages, with launches projected for the 2030s or 2040s, but they represent the next major step in the search for life beyond Earth. Even with advanced telescopes and sensitive instruments, the interpretation of biosignatures is complex. A single molecule or spectral feature is rarely conclusive. Context is essential. The composition of the atmosphere must be understood in relation to the planet's size, temperature, stellar irradiation, geological activity, and the availability of raw materials. Models of planetary atmospheres, informed by physics, chemistry, and observations of solar system planets and exoplanets, are used to predict what combinations of gases are possible under different conditions and to assess whether a given observation is consistent with biology, geology, or photochemistry. False positives, where abiotic processes mimic biosignatures, are a significant concern. For example, oxygen can be produced by photodissociation of water and carbon dioxide on planets around M dwarfs, where intense ultraviolet radiation from flares can drive such reactions. Methane can be produced by volcanic activity or impacts. Distinguishing these scenarios requires not just a detection, but detailed characterization, repeated observations over time, and, ideally, observations of multiple biosignature candidates simultaneously. The diversity of life on Earth provides some guidance for what biosignatures might look like, but it also underscores the limitations of that guidance. All known life uses water as a solvent, carbon as a structural element, and DNA or RNA as genetic material, but this may reflect the specific conditions under which life arose on Earth rather than universal requirements. Life in different environments, under different chemical regimes, might use different molecules, produce different waste products, and leave different signatures. Speculative biochemistries have been proposed, such as life based on silicon instead of carbon, or life using ammonia or methane as a solvent instead of water. Silicon can form chains and structures analogous to organic molecules, but silicon-oxygen bonds are much stronger than carbon-oxygen bonds, making silicon-based polymers less flexible and less reactive, which may limit the complexity of silicon-based biochemistry. Ammonia is liquid at lower temperatures than water and could serve as a solvent on cold worlds. But it is less abundant than water in the cosmos, and its chemistry is less well understood in the context of biology. Methane is liquid at even lower temperatures and is abundant on Titan, Saturn's largest moon, where lakes and seas of liquid methane and ethane cover portions of the surface. Whether life could exist in such an environment, using hydrocarbons instead of water, is unknown, but it is a question that missions to Titan, such as the upcoming Dragonfly mission, aim to explore. The emergence of life on Earth, the transition from non-living chemistry to living organisms, is one of the deepest unsolved mysteries in science. The earliest evidence of life dates to at least 3.5 billion years ago, possibly earlier, but the mechanisms by which life arose remain speculative. The leading hypothesis is that life began in an environment where the building blocks of biochemistry, amino acids, nucleotides, lipids, and sugars, could form and accumulate, and where energy sources were available to drive chemical reactions. Possible environments include hydrothermal vents on the ocean floor, where hot, mineral-rich water mixes with cold seawater, creating chemical gradients and providing energy in the form of redox reactions, or shallow tidal pools where cycles of wet and dry conditions could concentrate organic molecules and promote polymerization. Laboratory experiments have shown that amino acids and other organic molecules can form from simple starting materials like water, methane, ammonia, and hydrogen under the influence of energy sources such as ultraviolet light, lightning, or heat, a result first demonstrated in the Miller-Urey experiment in the 1950s. More recent experiments have explored the synthesis of RNA, a molecule that can both store genetic information and catalyze chemical reactions, making it a candidate for the first self-replicating molecule, the foundation of an RNA world that preceded the DNA-protein world of modern life. If life can arise from chemistry under the right conditions, then the universe may be teeming with life, as the building blocks are ubiquitous, found in comets, asteroids, and interstellar clouds, delivered to planetary surfaces by impacts and synthesized in situ by various processes. On the other hand, the step from chemistry to biology may require conditions that are rare or difficult to achieve, such as specific mineral surfaces that catalyze key reactions, particular combinations of elements in the right proportions, or long periods of stable, moderate conditions that allow complex molecules to accumulate without being destroyed by radiation, impacts, or chemical degradation. The fact that life arose on Earth relatively quickly, within a few 100 million years of the planet becoming habitable, suggests either that the process is not extraordinarily difficult, or that Earth was fortunate, one of perhaps billions of planets where the right conditions aligned. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them, looms over the search for life. If life is common, and if some fraction of life evolves into intelligent, technological civilizations, then the galaxy, which is billions of years older than Earth and contains hundreds of billions of stars, should be filled with evidence of such civilizations, whether in the form of radio signals, megastructures, or even visitation. The absence of such evidence has prompted numerous explanations, ranging from the possibility that intelligent life is extremely rare, that civilizations self-destruct before they can expand into the galaxy, that the timescales for exploration or communication are far longer than the lifetimes of civilizations, or that advanced civilizations deliberately avoid contact or are undetectable by current technology. Another explanation is that life is common but intelligence is rare, that the transition from simple life to complex, multicellular life, or from complex life to intelligent, tool-using life, involves bottlenecks that are unlikely to be crossed. On Earth, complex multicellular life took billions of years to emerge, and intelligent life is a recent development, appearing only in the last few million years out of 4.5 billion. The evolutionary path to intelligence may depend on a series of improbable events, such as the development of photosynthesis, the oxygenation of the atmosphere, the emergence of eukaryotic cells with mitochondria, the colonization of land, and the development of social behavior and language. The search for techno-signatures, evidence of technology produced by intelligent civilizations, is a complementary approach to the search for biosignatures. Techno-signatures could include radio or optical signals, the waste heat from large-scale energy generation, or the chemical signatures of industrial pollution in a planet's atmosphere. Gases like chlorofluorocarbons, which are produced industrially on Earth and have no known natural sources, would be unambiguous evidence of technology if detected in an exoplanet atmosphere. The detection of such gases is within the capabilities of telescopes like the James Webb Space Telescope. At least in principle, though the concentrations would need to be high and the planet would need to transit a bright, nearby star for the signal to be detectable. No techno-signatures have been detected to date, but the search is in its early stages, and the absence of evidence is not evidence of absence, particularly given the limited number of systems surveyed and the narrow range of signals that have been searched for. The structure of the universe, the distribution of galaxies, stars, and matter on the largest scales, sets the stage for the existence of planets and life. The universe began in the Big Bang about 13.8 billion years ago, an event that produced space, time, energy, and the simplest elements, hydrogen and helium, with trace amounts of lithium and beryllium. In the first few 100 million years, gravity pulled matter together into the first stars, massive objects that fuse hydrogen into helium and helium into heavier elements like carbon, oxygen, and iron. These stars lived fast and died violently, exploding as supernovae and dispersing their enriched material into the surrounding gas, seeding the next generation of stars with the heavy elements necessary to form rocky planets. Over billions of years, successive generations of stars have continued this process of nucleosynthesis and enrichment, gradually increasing the metallicity of the universe. The solar system formed from a cloud of gas and dust that was already enriched by earlier stars, and it is this enrichment that allowed Earth and the other rocky planets to form. Galaxies are the fundamental building blocks of a universe on large scales. Vast collections of stars, gas, dust, and dark matter bound together by gravity. The Milky Way, the galaxy that contains the solar system, is a barred spiral galaxy with about 200 billion stars, arranged in a flat disk with spiral arms and a central bulge, surrounded by a diffuse halo of old stars and globular clusters. The Sun is located about halfway out from the center in a relatively quiet region between spiral arms, a location that may be favorable for habitability. The central regions of galaxies, where stars are densely packed and supermassive black holes reside, are more hazardous, with higher rates of supernovae, gamma-ray bursts, and stellar encounters that could disrupt planetary systems. The outer regions of galaxies, where star formation is less active and metallicity is lower, may lack sufficient heavy elements for rocky planet formation. The galactic habitable zone is a concept analogous to the habitable zone around a star, a region of the galaxy where conditions are most favorable for the emergence and persistence of life, and it is thought to be an annular region at intermediate distances from the galactic center. Cosmic structures on even larger scales include galaxy clusters, superclusters, filaments, and voids, the cosmic web that traces the distribution of matter throughout the universe. Galaxy clusters are gravitationally bound collections of hundreds or thousands of galaxies, with masses dominated by dark matter and filled with hot gas that emits X-rays. Superclusters are loose associations of clusters and groups, spanning hundreds of millions of light years. Filaments are the largest structures, thread-like concentrations of galaxies and dark matter that stretch across the universe, connecting clusters and defining the edges of voids. Voids are vast regions, hundreds of millions of light years across, that contain few galaxies, almost no stars, and are the most underdense regions of the cosmos. The universe on the largest scales is not uniform but structured, a foam-like pattern shaped by gravity acting on the tiny density fluctuations that existed in the early universe, imprinted by quantum fluctuations in the first moments after the Big Bang. The expansion of the universe, discovered in the 1920s and confirmed by countless observations since, means that galaxies are moving away from each other, and the farther away a galaxy is, the faster it is receding. This expansion is not due to galaxies moving through space, but to space itself expanding, carrying galaxies along with it. The rate of expansion is quantified by the Hubble constant, and it has been increasing over the past few billion years due to dark energy, a mysterious component that makes up about 70% of the total energy density of the universe and exerts a repulsive force that accelerates expansion. The nature of dark energy is unknown, one of the biggest unsolved problems in cosmology, but its effects are observable, and it implies that the universe will continue to expand forever, eventually thinning out to a state where galaxies are isolated, stars cease to form, and the cosmos grows cold and dark over timescales of trillions of years. The matter content of the universe is dominated not by the ordinary atoms that make up stars, planets, and life, but by dark matter, a form of matter that does not emit, absorb, or reflect light, and is detected only through its gravitational effects. Dark matter makes up about 85% of the matter in the universe, and its presence is inferred from the rotation curves of galaxies, which show that stars in the outer regions of galaxies are moving faster than can be explained by the gravity of visible matter alone, and from gravitational lensing, the bending of light by massive objects, which reveals the distribution of mass in galaxy clusters and confirms that far more mass is present than can be accounted for by stars and gas. The particles that make up dark matter are unknown, though numerous candidates have been proposed, ranging from weakly interacting massive particles to primordial black holes formed in the early universe. Dark matter does not directly affect the chemistry or biology of planets, but shapes the large-scale structure of the universe and the formation of galaxies, and therefore indirectly influences the environments in which stars and planets form. Extreme astrophysical phenomena offer insights into the limits of matter and energy, and some have implications for habitability and the prevalence of life. Supernovae, the explosive deaths of massive stars, release more energy in a few seconds than the sun will emit over its entire lifetime, briefly outshining entire galaxies. A nearby supernova, within a few tens of light years, could bathe Earth in gamma rays and cosmic rays, damaging the ozone layer, increasing surface radiation, and potentially triggering mass extinctions. The fossil record shows evidence of possible supernova-related extinction events, though the connections are tentative. The rate of supernovae in the Milky Way is a few per century, and most occur far from the solar system. But over millions of years, the odds of a close encounter are not negligible. Supernovae also play a creative role, as they're the primary sources of elements heavier than iron, such as silver, gold, and uranium, which are produced in the extreme conditions of the explosion and ejected into space, enriching the interstellar medium and becoming incorporated into later generations of stars and planets. Gamma-ray bursts, the most energetic explosions in the universe, release as much energy in a few seconds as the sun will emit over billions of years, and they are visible across cosmological distances. They come in two types. Long-duration bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes, similar to supernovae but more extreme. Short-duration bursts, lasting less than 2 seconds, are associated with the merger of two neutron stars or a neutron star and a black hole, events that also produce gravitational waves, ripples in space-time that have been detected by observatories like LIGO and Virgo. A gamma-ray burst directed at Earth, even from thousands of light years away, could strip away the ozone layer and cause a mass extinction, but such events are rare and narrowly beamed, reducing the odds of a direct hit. The detection of gamma-ray bursts at high redshifts, meaning at great distances and therefore far back in time, indicates that they have been occurring throughout the history of the universe, and their energy and distribution provide constraints on models of stellar evolution and cosmology. Neutron stars, the remnants left behind after a supernova when the core of a massive star collapses but does not form a black hole, are among the densest objects in the universe, with masses around 1 to 2 solar masses compressed into a sphere only about 20 kilometers in diameter. The density is so high that protons and electrons are crushed together into neutrons, and the matter exists in states that cannot be replicated in any laboratory. Neutron stars rotate rapidly, with periods ranging from milliseconds to seconds, and they possess extremely strong magnetic fields, trillions of times stronger than Earth's. Some neutron stars emit beams of radio waves from their magnetic poles, and if the beam sweeps across Earth as the star rotates, the star appears to pulse, a phenomenon called a pulsar. Pulsars are extraordinarily precise clocks, and their timing can be used to detect gravitational waves, measure the properties of interstellar space, and test theories of gravity. Neutron star mergers, in addition to producing gamma-ray bursts, are thought to be the primary sources of elements like gold, platinum, and rare earth elements, which are produced in the extreme neutron-rich environment of the merger and ejected into space. Black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape, form when the core of a very massive star collapses during a supernova or when neutron stars merge. The boundary of a black hole, the event horizon, is the point of no return, and once matter crosses the horizon, it is lost to the outside universe. The physics inside the event horizon is governed by general relativity, and at the center lies the singularity, a point where the curvature of space-time becomes infinite and the known laws of physics break down. Black holes have been detected indirectly through their effects on nearby matter, such as the accretion of gas, which heats up and emits X-rays before disappearing into the hole, and through gravitational waves emitted during mergers. The first direct image of a black hole, or rather its shadow, was obtained in 2019 by the Event Horizon Telescope, a global network of radio telescopes that combine their signals to create an Earth-sized virtual telescope. The image showed the supermassive black hole at the center of the galaxy M87, a black hole with a mass of about 6.5 billion suns, surrounded by a glowing ring of hot gas. Supermassive black holes, with masses ranging from millions to billions of solar masses, reside at the centers of most galaxies, including the Milky Way, where a black hole of about 4 million solar masses, called Sagittarius A*, has been studied for decades through the orbits of stars that pass close to it. The formation of supermassive black holes is not fully understood, as the timescales required to grow from stellar mass seeds to supermassive sizes through accretion of gas seem longer than the age of the universe, suggesting that they may form through direct collapse of massive clouds in the early universe or through mergers of smaller black holes. Supermassive black holes play a role in galaxy evolution, as the energy released by accretion, which can outshine the entire galaxy, drives powerful winds and jets that blow gas out of the galaxy, quenching star formation and regulating the growth of the galaxy. This feedback is thought to be responsible for the observed correlation between the mass of a supermassive black hole and the properties of the galactic bulge, such as the velocity dispersion of stars. Quasars, short for quasi-stellar objects, are extremely luminous active galactic nuclei powered by supermassive black holes that are accreting matter at prodigious rates. They are among the most distant objects observable, with some detected at redshifts corresponding to when the universe was less than 1 billion years old, only a small fraction of its current age. The light from quasars has traveled for billions of years to reach Earth, and it provides a view of the universe as it was in the distant past. Quasars are also used as backlight sources to study the intervening gas between the quasar and Earth, as the gas absorbs light at characteristic wavelengths, leaving absorption lines in the quasar spectrum. These absorption lines reveal the distribution, temperature, density, and chemical composition of the intergalactic medium, the diffuse gas that fills the space between galaxies, and have been used to map the growth of cosmic structure and the reionization of the universe, the process by which the first stars and quasars ionized the neutral hydrogen that filled the universe after the Big Bang. The cosmic microwave background, the radiation left over from the Big Bang, is the oldest light in the universe, emitted when the universe was about 380,000 years old, after it had cooled enough for protons and electrons to combine into neutral hydrogen atoms, making the universe transparent for the first time. Before this epoch, called recombination, the universe was a hot, dense plasma where photons were constantly scattered by free electrons, preventing light from traveling long distances. After recombination, photons could travel freely, and this radiation has been redshifted by the expansion of the universe into the microwave portion of the spectrum, with a nearly perfect blackbody spectrum corresponding to a temperature of about 2.7 Kelvin. The cosmic microwave background is nearly uniform across the sky, but contains tiny fluctuations, variations in temperature of about 1 part in 100,000, that reflect the density fluctuations in the early universe for which galaxies and large-scale structures later grew. These fluctuations have been mapped in exquisite detail by satellites, such as the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory, and their statistical properties provide precise measurements of cosmological parameters, such as the age, composition, and geometry of the universe. Infrared astronomy has been essential to much of the progress in understanding the universe, as infrared light penetrates dust that obscures visible light, allowing observations of star-forming regions, the centers of galaxies, and the early universe. Dust composed of microscopic grains of silicates, carbon, and ice is ubiquitous in space, and it absorbs visible and ultraviolet light, heating up and re-radiating the energy in the infrared. Star-forming regions, where dense clouds of gas and dust collapse to form new stars, are often opaque at visible wavelengths, but they glow brightly in the infrared, revealing the embedded protostars, the disks of material swirling around them, and the jets of gas ejected from the poles of the forming stars. The James Webb Space Telescope, with its infrared capabilities, has imaged these regions in unprecedented detail, resolving individual protostars and disks, and providing insights into the processes that govern planet formation. The early universe, beyond a redshift of about 6 or 7, corresponding to when the universe was less than 1 billion years old, is difficult to observe at visible wavelengths because the light emitted by stars and galaxies has been redshifted into the infrared by the expansion of the universe. The James Webb Space Telescope was designed to observe this epoch, the era of the first stars and galaxies, and it has already discovered galaxies at redshifts exceeding 10, possibly as high as 13 or 14, meaning their light was emitted when the universe was only a few 100 million years old. These galaxies are surprisingly bright and massive, challenging models of galaxy formation that predicted slower growth in the early universe. The observation suggests that either star formation was more efficient in the early universe, or that the first stars were more massive and luminous than typical stars today, or that supermassive black holes formed earlier and grew faster than previously thought. The data are still being analyzed, and each new discovery refines the understanding of how the first structures emerge from the primordial gas. The process of reionization, the transition from a neutral universe to an ionized one, was driven by the ultraviolet light from the first stars and quasars, which ionized the surrounding hydrogen. This phase change occurred gradually over several 100 million years, and it is recorded in the absorption spectra of distant quasars, which show a gradual decrease in neutral hydrogen with decreasing redshift. The James Webb Space Telescope is observing galaxies during the epoch of reionization, measuring their ultraviolet output and assessing their contribution to ionizing the universe. Understanding reionization is important because it marks the end of the cosmic dark ages, the period between recombination and the formation of the first stars, and it sets the stage for the formation of the galaxies, stars, and planets that exist today. The distribution of elements in the universe, the chemical enrichment over time, is a story written in the spectra of stars, galaxies, and the intergalactic medium. The first stars formed from gas that contained only hydrogen, helium, and traces of lithium are called population 3 stars, and they're thought to have been very massive, hundreds of solar masses, and very short-lived, only a few million years. These stars fused hydrogen into helium, helium into carbon and oxygen, and continued the fusion chain up to iron, producing the first heavy elements. When they exploded as supernovae, they dispersed these elements into the surrounding gas, enriching it and allowing the next generation of stars, population 2 stars, to form with slightly higher metallicity. Population 2 stars, which include the old stars in the galactic halo and globular clusters, have metallicities about 1% that of the Sun. Over billions of years, star formation, supernova explosions, and the winds from massive stars have continued to enrich the interstellar medium, leading to the formation of population 1 stars, like the Sun, with metallicities at or above the solar value. The solar system, and by extension Earth and life, are made from recycled stellar material, the ashes of stars that lived and died billions of years ago, a connection that underscores the deep link between astronomy, chemistry, and biology. The search for planets and the characterization of their environments requires not just observations of the planets themselves, but an understanding of the stars they orbit, the systems they inhabit, and the galaxy in which they reside. Each level of structure, from the planet to the star to the galaxy, imposes constraints and provides context. A planet around an M-dwarf in the galactic halo, far from the plane of the Milky Way, will have a different chemical composition, a different history of bombardment by comets and asteroids, and a different exposure to cosmic rays and supernovae than a planet around a sun-like star in the galactic disk. A planet in a dense star cluster, where stars are separated by distances of light months rather than light years, will experience close encounters, radiation from neighboring stars, and the possibility of material exchange or even capture by another star. A planet in a galaxy undergoing a merger, where gas is compressed and star formation is triggered, will face heightened rates of supernovae and gamma-ray bursts, increasing the hazards to life. The concept of a habitable galaxy, or a galactic habitable zone, extends the framework of habitability to the largest scales. Not all galaxies are equally conducive to life. Small, irregular galaxies have low metallicities and may lack sufficient heavy elements for rocky planet formation. Large elliptical galaxies, which contain mostly old stars and little gas, have minimal ongoing star formation and may not produce new planets. Galaxies undergoing active star formation or mergers may be too violent, with frequent supernovae and intense radiation fields. Spiral galaxies like the Milky Way, with ongoing but moderate star formation, a mix of old and young stars, and sufficient metallicity, appear to be the most favorable environments. Within such galaxies, the habitable zone is thought to be an annular region at intermediate distances from the center, where metallicity is high enough for planet formation, but supernova rates and radiation levels are not excessive. The question of whether the universe is fine-tuned for life, whether the fundamental constants of nature are set to values that permit the existence of stars, planets, and complex chemistry, is a subject of philosophical and scientific debate. Small changes in the values of constants, such as the strength of the gravitational force, the mass of the electron, or the energy levels of atomic nuclei, could result in a universe where stars do not form, where carbon and oxygen are not synthesized, or where atoms do not bind into molecules. The fact that the constants have values that allow for a rich, complex universe has been interpreted in various ways. Some argue that it is evidence of a multiverse, a vast ensemble of universes with different constants, and we find ourselves in one where the constants permit life because only such universes can produce observers. Others argue that the constants are not arbitrary, but are determined by a deeper theory of physics that has yet to be discovered. Still others contend that the range of constants that permits some form of complexity is broader than often assumed, and that alternative chemistries and structures could arise under different conditions. Life, from the perspective of physics and chemistry, is a process that locally decreases entropy, creating order and complexity at the expense of increasing entropy elsewhere, typically by consuming energy from the environment. Thermodynamically, life is a far-from equilibrium system, sustained by flows of energy, whether from sunlight, chemical reactions, or heat. The emergence of life requires an energy source, raw materials, liquid solvent, and conditions that allow for the formation and replication of complex molecules. These requirements are not unique to Earth, and they could, in principle, be met on countless worlds across the universe. The universe is vast, with an estimated 2 trillion galaxies, each containing hundreds of billions of stars, and if even a small fraction of stars are planets, and a small fraction of planets are habitable, the number of potentially habitable worlds is staggering, numbering in the billions in the Milky Way alone and trillions across the observable universe. Yet the observable universe is only a portion of the total universe. The universe extends far beyond the region that can be observed, as light from more distant regions has not had time to reach Earth, given the finite age of the universe and the finite speed of light. The observable universe is a sphere roughly 93 billion light-years in diameter, but the total universe could be far larger, possibly infinite. And if it is infinite, then every possible configuration of matter, every possible planet, every possible form of life exists somewhere, repeated infinitely many times. The notion of an infinite universe with infinite possibilities is both humbling and dizzying, and it underscores the limitations of what can be known through observation, as only a finite portion is accessible. The exploration of the universe, the search for habitable worlds, the detection of biosignatures, and the quest to understand the nature of life and its place in the cosmos are endeavors that span centuries and involve the collective efforts of thousands of scientists, engineers, and institutions. Each new telescope, each new detection method, each new theory and model builds on what came before, gradually expanding the frontier of knowledge. The process is slow, often frustrating, marked by setbacks and false starts, but also by moments of profound discovery that reshape understanding. The detection of exoplanets, the characterization of their atmospheres, the discovery of habitable zone worlds, and the insights provided by the James Webb Space Telescope are milestones in this journey, but they are not endpoints. They are steps, each revealing new questions, new mysteries, and new directions for exploration. The James Webb Space Telescope has observed not only exoplanets, but also the distant universe, the atmospheres of solar system bodies, the formation of stars, and the structures of galaxies. Its infrared vision allows it to see through dust, to detect faint heat signatures, and to reach back in time to the earliest epochs of cosmic history. Among its observations are detailed spectra of the atmosphere of Jupiter, revealing the distribution of water, ammonia, and other gases, and providing insights into the dynamics of the giant planet's atmosphere. It has imaged Saturn's rings in unprecedented detail, showing the structure and composition of the ice particles. It has observed the plumes of water vapor erupting from Enceladus, Saturn's icy moon, confirming that the subsurface ocean is ejecting material into space, where it can be sampled by spacecraft or even by Webb's instruments if the geometry is favorable. Webb has also observed Titan, Saturn's largest moon, a world with a thick nitrogen atmosphere, methane lakes, and complex organic chemistry driven by sunlight. Titan's surface is hidden beneath a perpetual haze, but infrared light can penetrate the haze to some degree, revealing surface features and atmospheric composition. Webb's observations have detected new molecules in Titan's atmosphere, including complex organics that may be precursors to the building blocks of life, and they have provided data on the temperature and wind patterns in the upper atmosphere. Titan is considered one of the most promising locations in the solar system for the search for life, not life as it exists on Earth, but perhaps life adapted to cold, hydrocarbon-rich environments, using methane as a solvent and a different biochemistry altogether. The upcoming Dragonfly mission, a rotorcraft that will fly through Titan's atmosphere and land at multiple sites, will explore this possibility directly, analyzing surface samples for organic molecules and signs of biological or prebiotic chemistry. The study of solar system moons, particularly those with subsurface oceans, has become a major focus of astrobiology. Europa, one of Jupiter's large moons, has a surface of water ice crisscrossed with fractures and ridges, and beneath the ice lies a global ocean tens of kilometers deep, kept liquid by tidal heating from Jupiter's gravity. The ocean is in contact with a rocky seafloor, where hydrothermal vents could provide energy and nutrients, creating environments analogous to the deep-sea vents on Earth where life thrives in the absence of sunlight. The Europa Clipper mission, scheduled to launch in the near future, will orbit Jupiter and make dozens of close flybys of Europa, mapping the surface, measuring the thickness of the ice, and analyzing plumes of water vapor that may be venting from the ocean through cracks in the ice. If these plumes contain organic molecules or other signs of life, they could be detected by the spacecraft's instruments, providing the first evidence of life beyond Earth without the need to land on or drill through the ice. Enceladus, a much smaller moon of Saturn, also has a subsurface ocean, and it is actively venting water vapor, ice particles, and organic molecules through cracks in the South Polar region. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through these plumes and detected water, salts, silica, and complex organic molecules, including some that are associated with life on Earth. The presence of silica suggests interaction between the ocean and a rocky seafloor, and the detection of molecular hydrogen indicates that hydrothermal reactions may be occurring, providing a potential energy source for life. Enceladus is considered one of the highest priority targets for future missions, as its plumes offer direct access to the ocean's composition without the need for a lander or driller. Ganymede, the largest moon of Jupiter and the only moon known to have its own magnetic field, also likely has a subsurface ocean, and it will be explored by the European Space Agency's JUICE mission, which will orbit Jupiter and make detailed observations of Ganymede, Europa, and Callisto. The detection of subsurface oceans on multiple moons has broadened the concept of habitable environments, showing that liquid water can exist far beyond the traditional habitable zone, sustained by tidal heating or other internal energy sources. If life can exist in these environments, then the number of habitable worlds in the solar system and beyond may be far greater than previously imagined, as ice-covered ocean moons could be common around gas giants throughout the galaxy. The diversity of environments in the solar system, from the scorched surface of Mercury to the icy plains of Pluto, from the volcanic activity of Io to the hydrocarbon lakes of Titan, demonstrates the range of conditions that planets and moons can exhibit. Each body is a natural laboratory, a place where processes can be studied that cannot be replicated on Earth or in laboratories, and each provides insights into the physics, chemistry, and geology that govern planetary systems. The solar system is also a testbed for technologies and methods that will be used to study exoplanets, as the techniques developed to analyze the atmospheres of Jupiter or Titan can be adapted to analyze the atmospheres of distant worlds, and the lessons learned from studying the geology and climate of Mars can inform models of exoplanet surfaces and climates. Mars, the fourth planet from the Sun, has been a focus of exploration for decades, driven by the possibility that it once had conditions suitable for life. The surface is cold and dry today, with an average temperature of about -60 degrees Celsius and a thin atmosphere composed mostly of carbon dioxide, but there is abundant evidence that liquid water once flowed across the surface, carving valleys, forming lakes, and possibly creating oceans. Missions to Mars have discovered layered sedimentary rocks, mineral deposits that form in the presence of water in ancient riverbeds and deltas. The climate of early Mars, billions of years ago, was warmer and wetter, though the mechanisms that maintain this climate, given the faintness of a young sun, are still debated. Possible explanations include a thicker atmosphere with more greenhouse gases, volcanic outgassing of carbon dioxide and methane, or impacts that delivered water and volatiles. The loss of Mars' atmosphere, which allowed the climate to cool and the water to freeze or escape, is attributed to the loss of the planet's magnetic field, which disappeared early in its history as the core cooled and convection ceased. Without a magnetic field, the solar wind stripped away the atmosphere over millions of years, a process that continues today at a slow rate. Mars today is a world where the search for life focuses on the subsurface, where ice exists and where conditions might be more hospitable than on the surface. Recent detections of possible subsurface lakes beneath the polar ice caps, based on radar observations, have sparked interest, though the nature of these features is still uncertain. The Perseverance rover, currently exploring Jezero Crater, a site that once contained a lake, is collecting samples of rock and soil that will eventually be returned to Earth by a future mission, where they can be analyzed for signs of ancient microbial life. Venus, often called Earth twin because of its similar size and mass, is a study in how a planet can evolve along a radically different path. Its surface temperature of about 470 degrees Celsius, hot enough to melt lead, is the result of a runaway greenhouse effect, where carbon dioxide in the thick atmosphere traps heat so effectively that the planet radiates far less energy than it receives from the sun. The surface pressure is about 90 times that of Earth's, equivalent to the pressure at a depth of nearly a kilometer underwater. Sulfuric acid clouds shroud the planet, and lightning storms rage in the upper atmosphere. Yet there are hints that Venus was once more Earth-like, with liquid water on its surface and a more temperate climate. Models suggest that Venus could have remained habitable for billions of years before the greenhouse effect took over, possibly triggered by volcanic outgassing, the loss of water to space, or a change in solar luminosity. The study of Venus's climate, atmosphere, and geology provides insights into how planets lose habitability and into the limits of the habitable zone. The inner edge of the habitable zone is defined by the point where a planet receives so much stellar radiation that water vapor dominates the atmosphere, leading to a moist greenhouse effect that accelerates water loss to space. As water molecules in the upper atmosphere are broken apart by ultraviolet light into hydrogen and oxygen, the hydrogen escapes to space, and the planet gradually loses its water. Venus is thought to have crossed this threshold, and the detection of very low water vapor in its current atmosphere, combined with high deuterium to hydrogen ratios, suggests that it once had far more water that has since been lost. Understanding where this inner edge lies for different types of stars is critical for assessing which exoplanets are truly habitable and which are too close to their stars to retain water. The outer edge of the habitable zone is defined by the point where a planet is so far from its star that carbon dioxide begins to condense out of the atmosphere, causing the greenhouse effect to collapse and the planet to freeze. On Earth, atmospheric carbon dioxide prevents this, but there is a limit to how much carbon dioxide can be sustained in an atmosphere before it condenses into dry ice. For planets orbiting cooler stars, the outer edge is closer to the star, and for planets orbiting hotter stars, it is farther out. The width of the habitable zone, the range of distances where liquid water is stable, depends on the star's luminosity, and for M-dwarfs, the zone is narrow, sometimes only a few million kilometers wide, whereas for sun-like stars, it spans tens of millions of kilometers. Planets with eccentric orbits, rather than circular orbits, experience variations in stellar heating as they move closer to and farther from the star during each orbit. High eccentricity can cause a planet to alternate between frozen and molten states, which may prevent stable climates and long-term habitability. Though some models suggest that planets with moderate eccentricity could have seasons more extreme than Earth's, but still permit liquid water for part of the orbit. The distribution of eccentricities among exoplanets is wide, with many planets having orbits that are significantly eccentric, a result of gravitational interactions during the formation and evolution of planetary systems. Binary star systems, where two stars orbit each other, are common in the galaxy, perhaps more common than single stars like the Sun planets can form in binary systems, either orbiting one of the stars in a close orbit, called an S-type or circumstellar orbit, or orbiting both stars at a greater distance, called a P-type or circumbinary orbit. The habitable zones in binary systems are more complex, as the planets receive light and heat from both stars, and the distances and relative brightnesses of the stars determine where liquid water can exist. Circumbinary planets, orbiting both stars, experience variations in stellar irradiation as the stars orbit each other, leading to complex seasonal patterns. Several circumbinary planets have been detected, including some in or near the habitable zones of their stars, and the study of these systems provides insights into planet formation and habitability in environments different from single-star systems like the Solar System. Triple-star systems and higher-order multiple systems are rarer, but not unknown, and the dynamics of such systems can be chaotic, with planets potentially being ejected or having wildly varying orbits. The stability of planetary orbits in multiple star systems depends on the masses, separations, and eccentricities of the stars, and only certain configurations permit long-term stable orbits for planets. The Alpha Centauri system, the closest star system to the Sun, is a triple system with two Sun-like stars, Alpha Centauri A and B, orbiting each other, and a distant red dwarf, Proxima Centauri, orbiting the pair. Proxima Centauri has at least one confirmed planet, Proxima Centauri B, a roughly Earth-mass planet in the star's habitable zone, though the planet's habitability is uncertain due to the star's activity and the likelihood of tidal locking. The proximity of the Alpha Centauri system makes it a prime target for future missions, possibly including interstellar probes that could reach the system within a human lifetime if propelled by advanced propulsion technologies like laser-driven light sails. Interstellar travel, the journey to other star systems, remains in the realm of speculation and long-term planning, as the distances are vast and the energy requirements are enormous. The nearest star, Proxima Centauri, is about 4.2 light-years away, meaning that light takes 4.2 years to travel from star to Earth. With current spacecraft propulsion, which relies on chemical rockets or ion drives, the journey would take tens of thousands of years. Breakthrough Starshot, a proposed project, envisions using powerful ground-based lasers to accelerate lightweight probes, equipped with light sails, to a significant fraction of the speed of light, perhaps 20%, which would allow a probe to reach Alpha Centauri in about 20 years. The technical challenges are immense, including the construction of lasers with gigawatt power output, the development of material for the sails that can withstand intense radiation, the miniaturization of instruments and communication systems, and the ability to transmit data back across light years. Yet the project illustrates that interstellar exploration is not fundamentally impossible, only extraordinarily difficult and expensive, and it may become feasible with advances in technology and international cooperation. The detection of biosignatures or technosignatures, if it occurs, will be one of the most profound discoveries in human history, fundamentally altering the understanding of life's place in the universe. But even a negative result, a thorough search that finds no evidence of life, would be significant, constraining the prevalence of life and informing theories about the emergence and evolution of complexity. The search is in its early stages, with only a handful of exoplanet atmospheres characterized in detail, and most of those are gas giants, not rocky planets. The next generation of telescopes, both ground-based and space-based, will expand the search, observing hundreds of rocky planets, many in the habitable zones of their stars, and building a statistical picture of how common potentially habitable worlds are and what fraction, if any, show signs of life. The extremely large telescope, under construction in Chile, will have a primary mirror 39 meters in diameter, making it the largest optical telescope ever built. It will be capable of directly imaging exoplanets, particularly large planets in wide orbits around nearby stars, and characterizing their atmospheres with high precision. The Giant Magellan Telescope and the 30-meter telescope, also under construction, will have comparable capabilities. These ground-based telescopes, despite the challenges of observing through Earth's atmosphere, offer advantages in size and flexibility, and they will complement space-based observatories like the James Webb Space Telescope in future missions. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field infrared surveys, mapping large regions of the sky and detecting thousands of exoplanets through gravitational microlensing, a technique where the gravity of a planet bends the light of a background star, causing a temporary brightening. This method is sensitive to planets at a wide range of distances from their stars, including planets in cold, outer regions where direct imaging and transit methods are less effective. The data will provide a census of planetary systems, revealing the distribution of planet masses, orbital distances, and system architectures, and informing models of planet formation and migration. The search for life is intertwined with the question of what life is, a question that has no universally agreed-upon answer. On Earth, life is characterized by metabolism, growth, reproduction, adaptation, and response to stimuli, but these criteria may not apply to all forms of life, particularly if life arises under different conditions or uses different chemistry. Viruses, for example, reproduce and evolve but do not metabolize on their own, relying on host cells to replicate, and whether they are considered alive is a matter of debate. Prion, infectious proteins that can replicate by inducing misfolding in other proteins, are even more minimal, lacking nucleic acids entirely, yet they exhibit a form of reproduction. The boundaries of life are fuzzy, and any definition is likely to be provisional, subject to revision in light of new discoveries. If life is detected on another world, the first question will be whether it is related to life on Earth, possibly spread by panspermia, the transfer of microorganisms between planets on meteorites ejected by impacts, or whether it represents an independent origin, a second genesis. The latter would be far more significant, as it would demonstrate that life is not a singular event, but a general phenomenon that arises wherever conditions permit. Comparing the biochemistry of such life to that of Earth's life would reveal whether the chemistry of life is universal, constrained by the properties of atoms and molecules, or whether it is contingent, dependent on the specific conditions and random events of a planet's history. The discovery of a second sample of life, even if it is microbial and simple, would provide a comparison point that could revolutionize biology, chemistry, and the understanding of the universe. The possibility of intelligent life elsewhere, of civilizations that have developed technology, language, and culture, raises questions that extend beyond science into philosophy, ethics, and the future of humanity. If intelligent civilizations are common, then the galaxy may be filled with them, and the lack of contact could indicate that they are widely separated, that interstellar communication or travel is impractical, or that civilizations are short-lived, collapsing or self-destructing before they can make contact with others. The Drake equation, formulated in the 1960s, is an attempt to estimate the number of active, communicative civilizations in the galaxy by multiplying together factors such as the rate of star formation, the fraction of stars with planets, the fraction of planets that are habitable, the fraction where life arises, the fraction where life becomes intelligent, the fraction where intelligence develops technology, and the average lifetime of a technological civilization. Each of these factors is uncertain, and the result spans many orders of magnitude, from 0 to millions of civilizations. The equation is less a tool for prediction than a framework for organizing thinking about the problem. The Great Filter is a concept that attempts to explain the Fermi paradox by proposing that there is a barrier, a filter, that prevents life from progressing from simple origins to advanced, spacefaring civilizations. The filter could be in the past, such as the emergence of life itself, the development of complex cells, or the transition to multicellularity, in which case humanity has passed the filter and the future is open. Alternatively, the filter could be in the future, such as the development of self-destructive technologies, environmental collapse, or the inability to achieve sustainable interstellar expansion, in which case the silence of the galaxy is ominous, suggesting that advanced civilizations do not last long. Determining where the filter lies, or whether it exists at all, is one of the central challenges of astrobiology and the search for extraterrestrial intelligence. The cultural and psychological impact of detecting life elsewhere, whether microbial or intelligent, would be profound. Religions, philosophies, and worldviews are built on assumptions about humanity's uniqueness and centrality, and the discovery that life exists elsewhere would challenge those assumptions, forcing a reevaluation of humanity's place in the cosmos. The response would likely vary widely, with some embracing the discovery as confirmation of the richness and diversity of the universe, and others viewing it as a threat or a diminishment of human significance. The protocols for announcing and responding to such a discovery are a subject of ongoing discussion among scientists, policymakers, and ethicists, though no binding international agreements exist. The process would need to balance transparency and the public's right to know with caution and the need to verify the discovery before making it public, as false positives could undermine trust and credibility. The study of habitability and the search for life are not merely academic pursuits, but are connected to deeper questions about the nature of existence, the origins of complexity, and the future of life in the universe. The Earth, with its biosphere, is the only known instance of a planet where life has not only arisen but has persisted, diversified, and profoundly altered the planetary environment. The history of life on Earth, from the first simple cells to the complex ecosystems of today, is a history of adaptation, extinction, innovation, and resilience, played out over billions of years against a backdrop of changing climate, shifting continents, asteroid impacts, and the slow brightening of the sun. This history is recorded in rocks, fossils, and the genomes of living organisms, and it provides the only detailed case study of how life interacts with a planet over geologic time. Understanding Earth's history and the processes that have maintained its habitability is essential for interpreting observations of exoplanets and for assessing their potential to host life. The Earth is not a static system, but a dynamic one, with cycles of carbon, nitrogen, water, and other elements that connect the atmosphere, oceans, crust, and mantle. These cycles are driven by energy from the sun, from the Earth's interior, and from the chemical potential stored in minerals and organic matter. Disruptions to these cycles, whether from volcanic eruptions, asteroid impacts, or biological evolution, have caused major shifts in climate and ecosystems, sometimes leading to mass extinctions, events where a significant fraction of species disappear over a geologically short time. 5 major mass extinctions have occurred in the past 500 million years, and each was followed by a recovery period where new species diversified and filled the ecological niches left vacant. The most recent mass extinction at the end of the Cretaceous period 66 million years ago was triggered by the impact of a large asteroid, which caused fires, tsunamis, and a prolonged period of darkness and cooling that wiped out the dinosaurs and many other species. But it also opened opportunities for mammals to diversify and eventually give rise to humans. The current era, sometimes called the Anthropocene, is marked by human activity as a dominant force shaping the planet, altering landscapes, changing the composition of the atmosphere, driving species to extinction, and modifying ecosystems on a global scale. The long-term consequences of these changes are uncertain, and whether humanity can navigate the challenges of climate change, resource depletion, and environmental degradation without triggering a collapse or a significant reduction in the planet's habitability is an open question. The study of exoplanets and the search for life elsewhere provide a broader context for understanding these issues, as they reveal the diversity of planetary outcomes and the factors that determine whether a planet remains habitable over billions of years or transitions into an inhospitable state. The notion of planetary stewardship, the responsibility to maintain and protect the habitability of Earth, is informed by the knowledge that habitable planets may be rare, that the conditions required for life are delicate, and that the loss of habitability, once it begins, may be difficult or impossible to reverse. Venus serves as a cautionary tale, a planet that may have been habitable but is now a hellish world. And Mars is another, a planet that once had liquid water but is now frozen and barren. The study of these planets, and of exoplanets with diverse climates and atmospheres, provides insights into the mechanisms that drive climate change, the feedbacks that can amplify or dampen perturbations, and the thresholds beyond which a planet enters a different state. The concept of the Gaia hypothesis, proposed by James Lovelock and Lynn Margulis, suggests that life on Earth has not merely adapted to the environment, but has actively regulated it, maintaining conditions favorable for life through feedback mechanisms. For example, the presence of oxygen in the atmosphere is maintained by photosynthesis, and oxygen, in turn, supports aerobic life and influences weathering and climate. The burial of organic carbon in sediments removes carbon dioxide from the atmosphere, cooling the planet, and volcanic outgassing returns carbon dioxide, warming the planet, creating a long-term balance. Whether this regulation is the result of intentional processes or emergent properties of a complex system is debated, but the idea underscores the interconnectedness of life and the planetary environment, a perspective that is relevant to understanding how life might influence the climates and atmospheres of exoplanets. Terraforming. The hypothetical process of transforming a planet to make it habitable for humans has been proposed for Mars, where the thin atmosphere could potentially be thickened by releasing carbon dioxide from the polar ice caps and subsurface reservoirs, warming the planet and allowing liquid water to flow on the surface. The challenges are immense, as the amount of carbon dioxide available on Mars is uncertain, and the loss of atmosphere to space would need to be compensated by ongoing replenishment. The timescales for terraforming are estimated in centuries to millennia, and the ethical questions are profound, particularly if Mars harbors any extant or extinct life, as terraforming could destroy or contaminate such life. The concept of terraforming, while speculative, forces consideration of what habitability means, whether it is defined by the needs of humans or by the potential for life in general, and whether the modification of planets is justifiable or desirable. The long-term future of life on Earth is constrained by the evolution of the Sun. As the Sun ages, it will continue to brighten, and in about 1 billion years, the increase in solar luminosity will cause the oceans to evaporate, leading to a runaway greenhouse effect similar to what occurred on Venus. The Earth will become uninhabitable for complex life, though microbial life may persist in subsurface or high-altitude environments for some time longer. Eventually, the Sun will exhaust the hydrogen in its core and expand into a red giant, with a radius that may engulf the Earth. The timescale for this is about 5 billion years, far longer than the age of human civilization, but it underscores the finite nature of habitability on any planet orbiting a Sun-like star. Life, if it is to persist beyond this, would need to migrate to other worlds, either within the solar system or beyond, a possibility that requires technology and foresight far exceeding current capabilities. The study of stellar evolution and the life cycles of stars is essential for understanding the long-term prospects for life in the universe. Stars like the Sun spend most of their lives on the main sequence, fusing hydrogen into helium in their cores. But this phase is only one stage in a longer process that begins with the star's birth in a molecular cloud and ends with its death, which for Sun-like stars is a gradual process of expansion, mass loss, and contraction into a white dwarf. More massive stars, and more violently, in supernova explosions that can briefly outshine entire galaxies, and the remnants of these explosions, neutron stars or black holes, are some of the most extreme objects in the universe. White dwarfs, the remnants of low to intermediate mass stars, are dense, hot objects about the size of Earth, but with masses comparable to the Sun, supported against collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain density. White dwarfs cool slowly over billions of years, gradually fading from white to yellow to red, and eventually becoming black dwarfs, cold, dark objects that emit no light, though the universe is not yet old enough for any black dwarfs to have formed. Planets can survive the red giant phase and continue to orbit white dwarfs, and some observations suggest that rocky material, possibly from disrupted asteroids or planets, is accreting onto white dwarfs, polluting their atmospheres with heavy elements. The detection of such material provides insights into the composition of planetary systems around white dwarfs and raises the possibility that planets in the habitable zones of white dwarfs, which are very close to the star due to the low luminosity, could exist, though they would have survived a harrowing journey through the red giant phase or would have formed from the debris left behind. Brown dwarfs, objects that are too massive to be planets but too small to sustain hydrogen fusion, occupy a middle ground between planets and stars. They form like stars from the collapse of gas clouds, but their masses, ranging from about 13 to 80 times that of Jupiter, are insufficient to ignite hydrogen fusion in their cores. Some brown dwarfs fuse deuterium, a heavier isotope of hydrogen, for a brief period early in their lives, but this process is short-lived, and brown dwarfs spend most of their existence cooling slowly, radiating away their residual heat. The coolest brown dwarfs have surface temperatures below room temperature, and their atmospheres contain water vapor, methane, and ammonia, similar to gas giants like Jupiter. The boundary between the most massive planets and the least massive brown dwarfs is not sharp, and the distinction is based more on formation mechanism than on mass. Brown dwarfs can have planets, and some observations suggest that planetary systems around brown dwarfs may be common, though the habitable zones would be extremely close to the brown dwarf, and the low luminosity would make detection and characterization challenging. Rogue planets, also called free-floating planets, are planets that do not orbit any star, having been ejected from their planetary systems through gravitational interactions or having formed in isolation from the collapse of small gas clouds. These planets drift through the galaxy, unbound to any star, and they are difficult to detect as they emit little light. Some rogue planets may be warm enough to retain atmospheres and even surface liquid if they have thick hydrogen atmospheres that trap heat from the planet's interior, a greenhouse effect powered not by a star, but by the residual heat of formation and radioactive decay. The number of rogue planets in the galaxy is uncertain, but models suggest that they could be numerous, possibly outnumbering stars. The possibility of life on rogue planets is speculative, as the lack of stellar energy would preclude photosynthesis, but chemosynthetic life, sustained by internal heat and chemical reactions, might be possible, particularly if the planet has a subsurface ocean. The cosmic perspective, the view of Earth and humanity as small parts of a vast, ancient, and largely indifferent universe, is both humbling and inspiring. It places human concerns and conflicts in a broader context, revealing them as transient and local against the backdrop of cosmic time and space. At the same time, it underscores the rarity and preciousness of life, the improbability of the conditions that allow it to exist, and the fragility of those conditions. The search for life beyond Earth is, in part, a search for context, for understanding whether life is a common feature of the universe or an anomaly, and whether intelligence and technology are inevitable outcomes of evolution or rare accidents. It is also a search for connection, for evidence that humanity is not alone, that other minds exist somewhere in the vastness, grappling with their own questions about existence and the universe. The tools and methods of this search are grounded in physics, chemistry, and astronomy, but the questions it raises touch on philosophy, theology, and the human need for meaning and purpose. The detection of a signal from an extraterrestrial civilization, or the discovery of microbial life on Mars or Europa, would not answer all questions, but would open new ones about the nature of the life found, its history, its relationship to Earth life, and its implications for the future. The process of exploration, the gradual accumulation of knowledge through observation, experimentation, and theory, is itself valuable, independent of any single discovery, as it expands the understanding of the universe and humanity's place within it. The James Webb Space Telescope, as an instrument, is a convergence of decades of scientific ambition, engineering innovation, and international collaboration. Its construction involved thousands of people, multiple countries, and institutions, and its design pushed the boundaries of what was technically feasible, from the folding mirror and sun shield to the cryogenic cooling systems and the precision optics. The telescope's deployment, which required the mirror segments and sun shield to unfold in space, was a process fraught with risk, as any failure could have rendered the observatory inoperable. But the deployment succeeded, and the telescope has been delivering data that meet or exceed pre-launch expectations. The science enabled by Webb is transformative, not only in the study of exoplanets, but across all areas of astronomy, from the formation of stars and galaxies to the structure of the early universe. And its legacy will endure for decades as the data are analyzed and reanalyzed, revealing new insights with each iteration. The atmospheres of distant worlds, as revealed by Webb and other telescopes, are not just collections of gases, but dynamic systems shaped by physics, chemistry, and potentially biology. The detection of molecules, the measurement of temperatures and pressures, and the mapping of weather patterns provide clues to the processes occurring on these planets, from photochemistry driven by stellar radiation to circulation patterns driven by heating and cooling, to possible biological activity that alters the chemical balance. Each observation is a piece of a puzzle, and the picture that emerges is one of immense diversity, of planets that are similar in some ways to those in the solar system, but different in others, and of environments that challenge assumptions about what planets can be like. The superhabitable planets, if they exist, are not necessarily better places for life in an absolute sense, but they may offer conditions that are more stable, more enduring, or more conducive to the emergence and persistence of complex ecosystems. The criteria for superhabitability, such as orbiting a Cade dwarf, being slightly larger than Earth, having higher surface temperatures and humidity, and possessing active tectonics, are based on reasoning about what factors enhance habitability, but they remain speculative until such planets can be observed in detail. The James Webb Space Telescope and future missions will test these ideas, characterizing the atmospheres and climates of planets that meet some or all of the criteria, and determining whether they are indeed more habitable, or whether the concept needs to be refined or discarded. The search for habitable and superhabitable planets is not only about finding places where life might exist, but about understanding the principles that govern habitability, the factors that make a planet capable of supporting life, and the ways in which those factors can vary across different stars, different planetary systems, and different epochs of cosmic history. The knowledge gained from this search informs not only astronomy and astrobiology, but also planetary science, climate science, and the understanding of Earth's own history and future. The connections between these fields are deep, and the study of exoplanets provides a laboratory for testing theories and models that are difficult to test with Earth alone. As observations accumulate and more exoplanets are characterized, patterns may emerge, revealing correlations between stellar properties, planetary properties, and the presence of atmospheres, water, or biosignatures. These patterns will inform the next generation of observatories and the selection of targets for detailed study. The goal is not merely to find one habitable planet or one biosignature, but to build a statistical understanding of how common such planets are, what fraction of them host life, and what the diversity of life might be. This understanding will shape the search for intelligent life, the design of missions to explore the solar system, and the long-term strategies for ensuring the survival and flourishing of life, whether on Earth or beyond. The universe, as it is understood through the lens of modern science, is a place of vast scales, immense energies, and profound mysteries. It is governed by physical laws that operate uniformly across space and time, laws that are accessible to human reason and observation. Yet it is also a place where much remains unknown, where the nature of dark matter, dark energy, and the conditions before the Big Bang are still subjects of speculation and research. The search for life is embedded in this larger quest to understand the universe, and it draws on the full toolkit of science, from quantum mechanics and general relativity to chemistry, geology, and biology. The cosmic microwave background, the gravitational waves from merging black holes, the light curves of distant supernovae, and the spectra of exoplanet atmospheres are all windows into the workings of the universe, each providing a different perspective, a different set of constraints on theories and models. The synthesis of these observations, the construction of a coherent picture that accounts for all the data, is the work of cosmology, and it is an ongoing process, continually refined as new observations challenge or confirm existing ideas. The future of astronomy and the search for life will be shaped by the tools that are developed and deployed, by the questions that are asked, and by the willingness to explore the unknown despite the risks and uncertainties. The James Webb Space Telescope is one such tool, and its contributions are already significant, but it is not the end of the road. Larger telescopes, more sensitive instruments, and new techniques will follow, each extending the reach of observation and the depth of understanding. Ground-based observatories, space missions, and even observatories on the moon or in deep space are being planned or proposed, each with specific capabilities tailored to answer particular questions. The exploration of the universe is a multi-generational endeavor, spanning centuries from the first telescopic observations by Galileo to the sophisticated instruments of today, and it will continue for centuries more as each discovery opens new avenues for inquiry. The search for life, for habitable worlds, and for understanding the nature of the cosmos is a quest that transcends individual scientists, institutions, and nations, and it is driven by a fundamental human curiosity, a desire to know what lies beyond the horizon, to understand the origins and destiny of existence, and to find out whether we are alone. The silence stretches outward, measured in light years and epochs, filled with stars whose light has not yet reached Earth, with planets that turn in darkness, with processes that unfold over timescales far exceeding human lifetimes. The observations continue, the data accumulate, the models refine, and the search persists, patient and methodical, guided by the faint signals that cross the void.